Stay tuned for one of my favorite reactions, one of the most underappreciated reactions, one of the most ninja-level reactions in the entire organic chemistry sequence. Get ready for Nitriles plus Grignards. Nitriles are an interesting breed of functional groups. Nitriles are technically an acid derivative alongside esters, aldehydes, and anhydrides, but nitriles don't look anything like those other groups. This nitrile plus Grignard reaction often comes at the end of the set of reactions that you learn of nitriles. And learning the reaction of nitriles often comes at the end of the acid derivative unit, the nucleophilic acyl substitution reaction. And by the time you're through the acyl substitution reactions, you're often tired, you're maybe a little bit confused, and now you gotta learn these reactions of nitriles, and nitriles don't look anything like esters, and how are we supposed to do the reactions here? It's okay, I get it. That's why I'm here. The one piece of advice I'll give you right here at the front is don't get confused by nitrogen. It reacts a lot like oxygen. So don't think of this as a carbon-nitrogen pi bond. Imagine it in your head with the same kind of reactivity as a carbon-oxygen pi bond. In a lot of respects, nitriles react very similarly to carbonyls. And that's good news. We know things about carbonyls. Carbonyls are electrophiles. They're electrophilic at the carbon, toward good, strong anionic nucleophiles. And guess what? Nitriles are electrophiles. They're electrophilic at carbon, towards good, strong anionic nucleophiles. Furthermore, we've seen reactions of carbonyls with Grignard reagents before, so we might be able to predict a little bit of this mechanism ahead of time. Organic chemistry is a logical science. It's a predictive science. Because we've seen carbonyls before, because we've seen Grignards before, we have the ability to logic and reason and predict the reaction of these functional groups we may have never seen in combination before. And that is very powerful. In terms of our reaction sheets, this is a reaction of nitriles and a preparation of ketone. Now, the preparation of ketone part might surprise you. There are no oxygens in our starting material, and there's an oxygen in our product. We'll talk about it when we get to the mechanism. The oxygen comes from water in the quench. The key to unlocking this mechanism is remembering that part of the story is forming an imine as an intermediate. Imines are likely functional groups we've seen before. Imines form when we react amines with aldehydes or ketones. And crucially, imines can be hydrolyzed. Our quench is hydrolysis conditions. When we form that imine, we will hydrolyze it in the quench, and that's how we get the ketone. Let's work through this mechanism and see how we turn the nitrile into the ketone. To start, we know things about nitriles. Nitriles react a lot like carbonyls, and we know things about carbonyls. Carbonyls are electrophiles. They're electrophilic at carbon, toward good, strong anionic nucleophiles. Looking at our reagent then, a Grignard reagent is a good, strong anionic nucleophile. It is strong enough to directly attack carbonyls, which means it's strong enough to directly attack a nitrile. So the first step of our mechanism is to break the carbon-magnesium bond. The electrons bounce through carbon and attack the nitrile carbon, kicking electrons up onto nitrogen. I'm using the bouncing arrow notation here. If your instructor's not using bouncing arrow notation, they really should be. I have a link in the description below to the video about bouncing arrows. Watch that video, send it to your instructor, and maybe it will convince them to use bouncing arrows. This step of the mechanism adds the ethyl group to the nitrile carbon, forming a double bond with a negative charge on nitrogen. Now, in the past, when we've had strong anionic nucleophiles with acid derivatives like esters or acid chlorides, the strong anionic nucleophile has reacted twice. The reaction of a Grignard with an ester makes a tertiary alcohol where the Grignard adds twice. And that's not what happens here. It can't happen here because nitrogen already has a negative charge. If a second Grignard were to add in, that would give nitrogen with a 2- charge. Nitrogen isn't going to have a 2- charge. That means we pause the mechanism at this point until all the Grignard has had a chance to react with all of the nitrile. We're now ready for the quench. The first thing that happens is water gets protonated by sulfuric acid to form H3O+. The negatively charged nitrogen will then be protonated by that H3O+ that we just formed. That neutralizes the nitrogen and makes that imine intermediate. In some respects, this is kind of the end of the formal reaction of a nitrile with a Grignard. We added the Grignard, we neutralized the charge, we made a neutral molecule. So one way I kind of like to think about this is the nitrile plus the Grignard. We're going to pick up from here and hijack the imine hydrolysis mechanism to complete out the mechanism to form the ketone. Acid and water is hydrolysis conditions. I have a whole playlist on hydrolysis that I'll link to down below. Hydrolysis is kind of a magic phrase in organic chemistry that turns functional groups back into the parent of their class. Imines are at the 2-CZ bond oxidation level, so hydrolysis of the imine turns it back into the parent of that class, which is a ketone. For the hydrolysis part of this mechanism, the nitrogen picks up the proton from another molecule of H3O+, we're in acidic conditions, and from here we follow the story of the carbonyls. If you're not familiar with the story of the carbonyls, it's a concept I invented to help us organize all of our carbonyl-containing reactions in organic chemistry. I've also got a link to that video down below. Water is a weak neutral nucleophile. It can't directly attack a carbon-nitrogen double bond, but by protonating it, we've made it more electrophilic so that even a weak neutral nucleophile can attack. That forms our tetrahedral intermediate. In this intermediate, water is the best leaving group. I don't want water to be the best leaving group. I just added it in. I kind of want it to stay. I kind of want nitrogen to be the best leaving group. So I need to do the proton shuffle, where I shuffle the proton off of the group I want to stay and put the proton on the group I want to leave. To do that, we'll use more water to take the proton off of the group that I want to stay in the molecule and shuffle the acidic proton to the group that we want to leave the molecule. After the proton shuffle, the nitrogen group is now the best leaving group. I can kick it out in a leaving group expulsion. Collapse a pair of electrons down from oxygen, kick out the nitrogen leaving group. That forms our carbonyl with an acidic proton, so we'll do one more proton transfer to the end, file the paperwork, clean up the charges, form our desired final ketone product. The reaction of a nitrile with a Grignard reagent forms an imine that's immediately hydrolyzed to its corresponding ketone. The last thing I want to emphasize here is just how underappreciated this reaction is as a ninja skill. One of the most dreaded parts of an exam is the synthesis question, where you're given a molecule and said, go, synthesize this molecule using the reactions that you need to use. It's one of the more cognitively challenging parts of organic chemistry. I have a link in the description below if you'd like some more help on synthesis. To synthesize a complicated looking molecule like this, depending on where you are in the course, if you've learned about enolates, you might be trying to devise some kind of enolate alkylation strategy that would result in something like, 5 or 6 different steps. Or maybe you're more comfortable with epoxides and you think you might be able to get there through some kind of epoxide strategy. The nice thing about this reaction is it allows you to take this alkyl group and this alkyl group and stitch them together with a ketone in the center. Let me show you how. For this synthesis, we are going to target these bonds in this structure using the ketone at the center as our former nitrile. In a retrosynthetic sense, we might be able to make this ketone using our key nitrile and Grignard reaction. If the left side were a Grignard reagent and the right side was a nitrile, then suddenly my synthesis isn't this ridiculous looking thing, it's these two simpler things. Because if I can make these two simpler things, I can react them together, quench them under hydrolysis conditions to form the ketone I want to make. If you're not familiar with retrosynthetic arrows, I have a video that I'll link to down below that goes through all the arrows you're going to see in organic chemistry and explains what each one means. We've seen Grignard before. We know how to make Grignards. We make Grignards from the corresponding alkyl halides. And the cool part of this strategy is we know how to make nitriles too. Nitriles are also made from alkyl halides by taking a 1 carbon shorter alkyl halide and adding sodium cyanide in an SN2 reaction. And that's why this reaction is so cool. We can take this random alkyl halide and this random alkyl halide and stitch them together with sodium cyanide with hydrolysis to form a ketone. A very complicated looking ketone. So the way we might write out the solution to this synthesis reaction is to start with our alkyl halide and turn it into a Grignard using elemental magnesium. Making Grignards is probably something you've done dozens of times by this point in the course. Separately, we can take the alkyl halide that we need and do an SN2 reaction with sodium cyanide and a good SN2 solvent, like THF, to make our nitrile. And now for the cool part. We can take this nitrile, add that Grignard reagent that we just made, and then quench it under hydrolysis conditions. Using the mechanism that we just learned, the Grignard will attack the nitrile, form an imine. Hydrolysis conditions will hydrolyze that imine to form the very ketone that we are trying to make. And this is why this is such a cool reaction. 3 very short steps make a very complicated looking ketone with a lot of carbons in it. I would highly recommend keeping this reaction up your sleeve so you can be an OChemNinja. Here's our reaction card for the nitrile and Grignard reaction. The 3-phrase sentence for this reaction is a nitrile plus a Grignard makes a ketone. We need to know this 3-phrase sentence in all possible combinations. A nitrile plus a Grignard makes a ketone. A Grignard turns a nitrile into a ketone, and a ketone can be made when we react a nitrile with a Grignard. As a note for this reaction, it's a great way to make complex ketones. It's a nice complement to enolate alkylation reactions. Some tags for this reaction: it's non-regioselective. We're not choosing between reactive sites in the molecule. It's also non-stereoselective. The ketone that we're making isn't even a stereocenter. And it is a net reduction. The nitrile's at the 3 CZ bond oxidation level, and the ketone is at the 2 CZ bond oxidation level.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.